One of the more useful applications of calculus is finding extrema of functions. Very simply put, that means trying to find the highest and lowest points of a function. Now, just a note about the terminology here. Extremum, maximum, minimum, they all refer to the singular, one such point. Whereas extrema, maxima, minima, they all refer to plural, so multiple points. First thing that we're going to do is define, or what are called absolute or global extrema. These are meant to imply the highest or lowest points. I'm going to give a definition of this first. So the absolute maximum of a function f occurs at the point x equals c if the value of the function at that point is greater than or equal to the value of the function at any other point for all x in the domain of the function. The minimum would satisfy almost an identical definition, except that we would have f of c less than or equal to f of x. The two are almost identical, it's just that the direction changes. Now, in terms of a picture, when you are at an absolute maximum or a minimum, I am higher than any other point on this function along its entire domain. Now, similarly, if I had an absolute min, this point would be lower than every other point in the domain of the function. So when we talk about an extremum, there are two pieces of information. There's the location that we're interested in, and then there's the value or the height. So I'm going to give you several examples to give you some perspective on what to expect. If I were to give you the function x squared, f of x equals x squared does have an absolute minimum at the vertex of this parabola. So the location is 0, and the value of the absolute minimum is 0 as well. This is the lowest point in the graph of the function. There are no points lower than this. But there is no absolute maximum, because no matter what point I pick, if I just move over a little bit, I will be able to find a new point that is higher than the previous one. That means the definition cannot be satisfied. At the same time, if we talk about the exponential function, e to the x, for exactly the same reason, this has no absolute maximum. Because no matter what point I pick on this graph, if I were to move over a little bit, the graph will go up higher. And so I'll never be able to satisfy the definition. There will never be a point f of c that is higher than any other point in the domain. Is there an absolute minimum? There's a horizontal asymptote right at this point. And a horizontal asymptote means that I just get closer and closer to the value, in this case, of 0. So no matter what point I pick, if I slide over a little bit further, I will be able to find another point that's a little bit closer to 0 than the previous one. So in that sense, I will never be able to satisfy the definition of an absolute minimum either. Some functions have absolute extrema, some functions don't. Here's another very common function that you're all familiar with. So the sine function has a domain of all real numbers. Its range is between -1 and +1. So that means there are infinitely many different points where the function attains a height of -1. Is there an absolute minimum? The definition of an absolute extremum says less than or equal to, or greater than or equal to. It's that equal to that allows you to have multiple high points and low points. So we have infinitely many absolute minima at x equals pi over 2 and any n pi multiple of that. So n would be an integer. Oh, sorry, this should be happening not at pi over 2, but at 3 pi over 2. At the same token, we have many, many, many absolute maxima. This happens at x equals pi over 2 plus any 2 pi multiple of this. And I should say the same thing down here. This would happen at any 2 pi multiple of this. So infinitely many minima and maxima are possible. And we can take that idea to the extreme again. So if I were to take a function that's a constant, it's defined for all real numbers. Its graph is horizontal like this. Does this function have an absolute minimum? According to the definition, you have to pick a point, and if that point is less than or equal to the height of the function at any other point, it will be an absolute minimum. So regardless of what point you pick, according to the definition, every point is an absolute minimum. There are also infinitely many of them, but uncountably infinitely many. There are uncountably many points, so uncountably many absolute minima here. At the same token, you will have uncountably many absolute maxima. Every point is an absolute maximum. So we've spent a bit of time talking about absolute or global minima and maxima, the highest, the lowest. So what about other types of extrema? You might say, well, what other types are there? And as a nice example, here is a polynomial function, x cubed minus x. So this function can easily be factored. Why might you want to do that? Because the factorization will help you graph it. So from high school, you should have learned that this function crosses the x-axis in each of those places once. There is no absolute maximum for this function because no matter where I stand, I will be able to slide over and go a little bit higher. There is no absolute minimum for this function because no matter where I stand, I'll be able to slide down and go down a little bit further. You see that there's something interesting happening at these points. They aren't absolute minima or maxima, but they are in their neighborhoods the largest or smallest points. So those types of examples are also important. So we are going to define something called relative or local minima or maxima. We will say a function f has a local maximum at x equals c if f of c is greater than or equal to f of x for all x in some open interval containing x equals c. And at the same time, I can adjust that to read minimum. And just like before, the only adjustment would be a less than or equal to there. We are no longer talking about every single point in the domain. We are just talking about some points in the domain. An open interval in interval notation usually has round brackets. So you can imagine taking your hands and cupping it around a point. So for instance, if I were to take my hands and cup around this point, in this open interval, this point is higher than its local neighbors. Now, if I start making that open interval larger and larger, I'm eventually going to find some points that are higher than that. So I can't make the interval too big, but the definition doesn't care. It just says some open interval. If I were to cup my hands around this point, I can see that in that little neighborhood, it's lower than any other point. Now, I can't make that interval too wide because if I start going too wide, I will find another point that's lower. But that's okay. The definition says some open interval. This is also a bit of a sneaky definition, and students usually run into some headaches when they talk about this. So for instance, if I were to take f of x equals x on the interval 0 to 1, does this function have any extrema? Is there an absolute maximum right there? The answer is no, because no matter what point you pick, if you zoom in, if I were to say that is the absolute maximum, the point right before there are infinitely many points in here that are closer and higher than the one you chose. And no matter how much you zoom in, you will always be able to find more points between the one you picked. So you can never actually attain that. You can always get a little bit closer. And the same thing will happen down here. So there are no absolute or even relative minima or maxima in an example like this. If I were to take an example like this, does this function have absolute extrema? So it has no absolute minima, because no matter what I pick down here, the function will continue to drop. Does it have any maximum? The answer is again, no maxima of any kind. Because if I were to cup my hands in this interval, at this point, that won't count as an absolute maximum for the reasons that we mentioned above. However, that point right there is a relative minimum. Because if I were to cup my hands close enough, that point would be lower than any other point in this interval.